we've looked at so many examples of vector spaces that you might be wondering if everything is a vector space. Well, of course not everything is a vector space. For one thing, remember we looked at an example of all of the polynomials of degree exactly n, and we decided that, well, this isn't closed under vector addition, so this isn't a vector space. So not everything is a vector space, but you might be suspect about this because polynomials, who knows what they're even about. What about solution sets to linear equations, though? Well, here's a non-homogeneous system of linear equations. We could ask, does the collection of solutions to this system form a vector space? Well, it's hard to tell in general, but what you might try is find a solution to this equation. I happen to see one because I made this system easy to solve. 1, 1 is a solution to this system, right? If you plug this 1 in for x and for y, it satisfies both equations. So this is a solution. All right, so if the collection of solutions to this system were a vector space, then adding another solution to this would have to give us yet another solution. Well, we only know the one solution, but we could always try adding it to itself. That would give us 2, 2. So 1, 1 is a solution. 1, 1 is also a solution because it's the same solution. So now we need to ask, is 2, 2 a solution? Well, clearly not. If you just plug it in, it doesn't work, right? 2 plus 2 is 4, not 2. So the answer here is no. So for this homogeneous system, the solutions do not form a vector space. Of course, you could wonder in general, are there any non-homogeneous equations where the solutions form a vector space? And the answer is no. You can see that if you have a non-zero solution, right? So if you have, let me write it like this: a11 x1 down to a1n xn equals b1, and then am1x1 plus amn xn equals bn, right? If you have a solution, say v1 down to vn, right, a value for each one of these variables, then if you add it to itself, what you get is twice what you started with. Okay, fair enough. Now the question is this a solution? But it can't be, because when you plug it into any one of these equations, I'll plug it into just the first one, right? We're plugging in this vector, so its first entry is 2v1 plus, and so on, down to a1n 2vn. What does this give you? Does it give you b1? Well, you see every term here has a factor of 2, so let's factor out the 2. Then we get a11 v1 plus so on, down to a1n vn. Okay, but what is all this stuff in parentheses? Well, remember, the vector of v's is a solution to this system. That's what we assumed. And so this stuff in parentheses is just the left-hand side of this equation with the v's plugged in. So that means it has to be equal to the right-hand side of this equation, so b1. So is this vector a solution? Well, if you plug it in, it doesn't give you b. It gives you 2. It doesn't give you b1. It gives you 2 times b1. So is 2 times b1 equal to b1? Only if b1 is 0. But this same argument works for every equation in this system. So the only way that, if you have one solution, the only way for twice that to be another solution is if all of your b's are 0. But in that case, it's a homogeneous system, not a non-homogeneous system. So the upshot of all of this is that for homogeneous systems, the collection of solutions is never a vector space. So, as for all the vector spaces we got by knowing that homogeneous systems give you vector spaces for their solutions, non-homogeneous systems give us an equally numerous number of non-vector spaces. Any collection of solutions to a non-homogeneous system will be a non-homogeneous or a non-vector space.